We're now going to cover the template method pattern. In this discussion, you'll not only understand how the template method pattern works in general, but you'll also learn to recognize how this pattern can be applied to support multiple operating modes in the expression tree processing application. The purpose of applying this particular pattern is to simplify the processing of multiple operating nodes by allowing controlled variability of steps in an algorithm. Let's talk a bit about how we can apply this pattern in the context of the expression tree processing app. As you may recall from the case study discussion in Lesson 2, this app has two primary operating modes, verbose mode and succinct mode. In verbose mode, users type in command operations directly, either through a command line or via a graphical user interface. In succinct mode, all users have to do is simply provide an expression, and everything else is handled internally. Needless to say, we'd like to figure out a way to avoid structuring the program so we don't hard code it in terms of these two operating modes. Because if we do this, it's going to lead to several problems. Problem number one is we'll end up incurring many of the same limitations that we did with our original algorithmic decomposition. For example, structuring the program in terms of the algorithms will end up putting the complexity in the variable algorithms rather than in the stable structure. The other problem has to do with what will happen to the maintenance and evolution of the code base if we end up partitioning the solution into two separate algorithms. In particular, if we have a verbose mode algorithm implementation and a succinct mode algorithm implementation, and they don't share very much in common, then any bug fixes or improvements that we add to one won't easily be reused without additional work in the other one we already have. So what's the solution we're going to apply? We're going to end up encapsulating algorithm variability by implementing the core algorithm once in a base class and then letting subclasses define variants of the solution. Take a look at the slide, for example. You'll see we have an input handler class that has a method called handleInput. And this method is what's known as a template method. And as you can see, the template method defines a number of calls or steps to so-called hook methods. The order and the steps that are invoked is fixed in the template method. But since each of those calls is to a virtual method, we can allow those methods to be selectively overridden by subclasses. And in particular, we can define a verbose mode input handler and a succinct mode input handler, both of which inherit from input handler, and they can selectively override the methods they choose to get the different behaviors that correspond to the differences in the two operating modes. For example, verbose mode simply has the make user command factory method called directly down to the user command factory's make user command method, passing along the input. So not much going on there. In contrast, the succinct mode input handler does something a little different. What it does is it goes ahead and it prepends the string macro before the input, and that's used as an instruction to the user command factory to make a macro command, which combines multiple commands, as we've talked about in previous pattern discussions. The nice thing about using this particular approach is we increase the opportunities for systematic software reuse. We're going to reuse many of the same components and only have differences where there's actually divergence between the way in which the two algorithms work. And even there, as you can see, we're reusing many of the same components, just with very minor tweaks. So let's talk a bit about our input handler class. This is an abstract class that provides the boilerplate algorithm for controlling the operating modes of the expression tree processing app. There's a number of methods that are defined here. HandleInput is the core template method. We could have defined this method to be final, but we left it non-final to give ourselves a little leeway in case we decide to change the actual algorithm itself. But typically, the template methods don't need to be virtual at all. They can often be non-virtual. We then define a factory method called makeHandler that'll make the appropriate type of handler, be it succinct mode input handler or verbose mode input handler. And then we define a number of hook methods, some of which have default implementations, some of which are abstract. From a commonality and variability point of view, the input handler class defines a common interface for handling user input events and for performing the key steps in the expression tree processing algorithm. From a variability point of view, we have these different subclasses that implement the different operating modes, verbose versus succinct mode, and so on. Here's a diagram that just summarizes the classes in the input handler class hierarchy. We have the two subclasses that override some of the hook methods defined in the input handler base class in order to define succinct and verbose operating modes. The way in which we arrange these roles and responsibilities corresponds nicely to one of the patterns in the Gang of Four book called template method. The intent of this pattern is to provide a skeleton of an algorithm in a method, but deferring certain steps to subclasses. You should consider applying this pattern under a number of conditions. For example, you want to be able to implement invariant aspects of an algorithm once and then let the subclasses define the variant parts. Likewise, if you want to be able to localize common behavior in a class to increase code reuse, which is what we're doing here, and you want to be able to have a controlled way of allowing subclasses to extend and enhance and override some of the steps or all the steps in the basic invariant algorithm. Here's a diagram that illustrates the structure and participants in the template method pattern. As you can see, we have an abstract class which defines a number of methods. One of the methods is the template method, which may or may not be virtual, as we talked about before. What it does, however, is it calls a number of primitive operations, what I like to call hook methods. And these hook methods can be customized and overridden in a concrete class, or concrete classes as it may be. In our particular expression tree processing application, the abstract class is played by the input handler, and the concrete class role is played by the verbose mode input handler and succinct mode input handler. Let's take a look now and see how we could go ahead and implement this pattern in Java. The key idea is to define the algorithm once and then allow the subclasses to customize some of the steps. So you can see we have our input handler class, and that input handler class defines the handle input template method, and it's got 4 hook methods it calls out to. Those 4 methods involve prompting the user, getting the input from the user, making the user command based on the input, and then finally executing that command. Here's an example of a factory method we could use to create the appropriate type of input handler. If you pass in a Boolean verbose flag, that indicates you want to create the verbose mode input handler. And if you pass it in with the value of false, that means you want to create a succinct mode input handler. This isn't the only way or even the best way of defining a factory, but it's good enough for the purposes we're trying to do here. Here's an example of how we would implement verbose mode input handler, which extends input handler and overrides some of the methods. Here's one of the methods it overrides. It overrides the make user command hook method. And as you can see here, all it does is it simply takes the input expression that was passed by the user and it calls the make user command factory method on the user command factory, and that will return the corresponding command, be it a print command or format command or some other command. Here's the same method implemented in the succinct mode input handler. In this case, make user command forwards also to the user command factory's make user command method, except it prepends the word macro in the front of the user expression. And if you go and take a look at the implementation of the make user command method in the user command factory, you'll see that when the word macro appears first, that ends up causing the appropriate command implementation portion of the user command factory to implement a so-called macro command, which behaves differently from a non-macro command. Let's go ahead now and take a look at some of the code, and we'll walk through and illustrate how the template method pattern is used, and I'll illustrate some of the variations that apply within the application in our expression tree processing app. The implementation of the template method pattern in our expression tree processing app is broken up into several files. Let's start by taking a look at the core file, which is the input handler file. Input handler is an abstract class, and it contains a number of different data members and methods used to implement the template method pattern. For example, we keep track of the global input and the global output as objects. We keep track of whether we're verbose or not. We keep track of the tree ops that we're using to invoke operations on. We have a user command factory in order to make the various kinds of commands and so on. And all of these various fields are initialized in the constructor of input handler. We also define a very simple factory called make handler, which takes a number of parameters, and depending on whether we're running in verbose mode or not, returns the appropriate type of input handler, either verbose mode input handler or succinct mode input handler. This is not necessarily the best or the only way to implement this. It was just a way to keep it all consolidated in one place to keep the example fairly simple. I probably wouldn't have done this in real life if I had an extensible set of different kinds of commands, because this is a bit too hard-coded. Here then is the main template method that we have in input handler. This template method, as you can see, is called handle input, and it calls a series of hook methods to do its job. It calls prompt user, it calls retrieve input, assuming that we're still up and running. It calls make user command to make a user command. and it goes ahead and executes the command, and then before it drops out, it goes ahead and cleans a few things up. It prints valid commands and so on, which are useful to know what you're doing if you're running in verbose mode. So let's go take a look at some of these implementations of the hook methods and see how they're done. Prompt user is implemented as a purely abstract method. We leave it up to subclasses to figure out how to implement that method. Retrieve input will use the platform strategy to get the input that we were given by the user. Make user command is also an abstract method. This ends up being implemented in one of our two subclasses. But execute command can actually be given a reasonable default implementation. And what it does is it simply takes the command that was passed in and it goes ahead and executes it. So that's the basic core part of our input handler. Let's now go take a look at the two subclasses that we use with this. Verbose and succinct mode input handler. Here's verbose mode input handler. As you can see, verbose mode input handler extends input handler, so it inherits all of its state that's public and protected, and it also inherits its methods. Here's the prompt user hook method for verbose mode. As you can see, it goes ahead and puts a number of things out there. And it also uses our platform strategy in order to be able to abstract away from whether we're doing the output here on the Android platform or in the command line environment. So that's what the prompt user method does. Here's what the make user command method does for verbose mode. It simply turns around and forwards to the user command factory, calling its make user command on the user input. We looked at this implementation when we talked about the factory method pattern earlier, so you can go back and see how that works if you want to remember how make user command works. That's verbose mode. Now let's go ahead and take a look at succinct mode. Here's succinct mode's implementation. It also inherits or extends input handler. Its prompt user implementation is a little different, however, because keep in mind that for verbose mode we had a lot of stuff to print. For succinct mode, we're just going to print out a prompt. So it turns out if we happen to be running in the command line platform, then we're simply going to print out a very simple prompt, which is the greater than symbol. Notice again our use of the strategy pattern to abstract away from the details of the underlying platform. The make user command method is a little bit different than verbose mode. As you can see, what we do is we take the user input expression and we prepend the macro prefix to it as a string. And this macro prefix will then be used later by the user command factory to make a macro command. In fact, just for fun, let's go over and look real quick at the user command factory, and we'll look up macro, and you'll see here's what happens when the macro command is used. So if a macro command is used, it creates a new iUser command factory command whose execute method implements the macro command execution creation, which turns around and creates a new vector of user commands, and it goes ahead and it makes a format command with in-order format designation, makes a new expr command passing in the expression created as a string, and then it goes ahead and it creates a new eval command using the post-order evaluation model. And it takes all of these three things, and then it makes a new macro command passing in the macro command's vector as the parameter to this. And if we go over here real quick and take a look at macro command, you'll see that macro command is a user command, and what it does when its execute method gets called is it iterates through every commands in the macro command parameter, which is that vector that was passed in to the constructor, and it calls execute on each of them. So this will, of course, popping back off a second, it'll go ahead and create a new format command for in-order processing, create a new expression command, and then create a post-order traversal, and it'll run all of those things one at a time. So it basically allows us to be able to combine multiple activities in succinct mode that would have had to have been done one command at a time in verbose mode. So that's a nice example of how we use this particular set of patterns in order to be able to implement the make user command hook method in the context of our template method. Now that we're done looking at that code, let's go ahead and talk about some of the consequences of applying this pattern. Template method has a number of benefits. One of the nice things it does is it enables inversion of control, which is crucial for frameworks which want to own the event loop and call back to registered objects or services or handlers when interesting things occur. Inversion of control is often referred to as the Hollywood principle, which says, don't call us, we'll call you. And you can see here how our implementation uses this to drive the main event loop. We have an input dispatcher, which goes ahead and dispatches one input or all inputs, and that ends up calling back to handle input, which in turn is the template method that calls the various hook methods to carry out the processing steps. Another nice thing you get from this pattern is the ability to be able to allow programmers to enforce the overriding rules via subclassing. You can decide what methods that are hook methods in the base class get modified and customized, or which ones get reused. It's up to you based on whatever capability or protocol or service you're trying to implement and customize in the subclasses. Another good benefit is it helps to promote additional code reuse by collapsing stovepipes. In contrast to an algorithmic decomposition, which would end up with the verbose mode and the sync mode algorithms being done distinctly as separate stovepipes with very little overlap, with our template method-based solution, there's a lot of common reusable code, and only the parts that actually differ, in other words, the make user command and prompt user methods, those are the only things that actually differ, and they differ in ways that are very clean and clear. We have a common interface to support extensibility and variability, which is very powerful. There are, of course, some downsides to this pattern. You have to subclass a base class in order to be able to vary the behaviors. And if you have a lot of hook methods that are called by your template method, and each of those hook methods has a number of different variations that it has to embody, the combination of all these different methods can lead to an explosion of subclasses. So we're going to compare and contrast this with the strategy pattern in just a minute to give you another way of looking at how to solve this type of problem without requiring such a large combinatorial number of subclasses. There's a number of implementation considerations. One of the questions that we've already touched on is whether or not to make the template method virtual or non-virtual, or final, as we'd say in Java. It really depends on whether the algorithms that are embodied by the template method itself may need to change in the future. If you know that they're never going to change, then make it non-virtual, make it final. If you aren't sure whether the algorithm steps may change, my recommendation is to use virtual. Another consideration is whether you want to have a few or many primitive operations, or what I'm calling hook methods. This, of course, is really up to you. What do you see as the steps in the algorithms that may vary? Do you want to provide fine-grained control, coarse-grained control, or whatnot? Once again, that's something that has to be decided based on your requirements and your understanding of the domain and the commonalities and variabilities that you understand at a particular point in time. There's also some minor issues about naming conventions. Do you call these methods make versus do or on? There are different ways you can do this. There's lots of known uses of this pattern. It's used a lot in user interface toolkits. It's used in the Java AWT toolkit. We use it a lot in the middleware we've developed. One of the more interesting uses of template method occurs in the Android async task framework. Async task is a framework that Android provides to allow the user thread to start operations that then run in one or more background threads. And what you do is you basically use a subclass of the async task class, where the async task class essentially plays the role of the template method portion. And then you go ahead and you can override the template method hook methods to do various kinds of things to determine where and how you're going to process the operations in threads that run in the background. For example, in the async task example, the execute method is the template method. You call execute when you want to run a task in the background. And then there's a number of hook methods that you can selectively decide to override. One's called on pre-execute, which is called prior to starting the task running in the background. One is called do in background, which, as the name suggests, is actually what runs in a separate thread in the background. There's also something called on post-execute, which will be running back in the main thread after you're finished. And then there's also something else called on process update, which gets run in the main thread also, taking results that get passed back from the operations running in the background. So this is a very interesting example of template method because it illustrates the concept of template method, but it also splits across concurrency boundaries. Let's briefly compare and contrast strategy with template method, because these patterns are really pattern complements. You can often choose one or the other. The arguments in favor of using strategy are that it provides more of a black box way of doing things. You don't use subclassing quite as intimately as you do with template method. You can also change the strategy implementation more dynamically at runtime, whereas with template method it's done more at compile time by inheritance. You can also mix and match different features more flexibly with strategy. The downside with strategy is you can end up with lots and lots of strategy classes, and there may be a bit of overhead for forwarding different operations. Template method, in contrast, doesn't necessarily require explicit forwarding, so it may be arguably a little bit faster in terms of runtime performance. And it may also be easier for small use cases. If you only have a couple of sources of variability, strategy can be overkill, and template method is easy to use. The downside with template method, however, as you get more complex variations, you end up having this subclass explosion we talked about before. And you also closely couple the subclasses and the base classes. So there's a bit more static, it's harder to reconfigure things at runtime, you've got more subclass explosion. In general, deep inheritance hierarchies are usually a red flag that you've got a bad code smell or something like that. So you have to decide which is best for you. We ended up selecting the use of template method in our case study since it's a fairly simple use case and we didn't want to have to create the whole machinery for the different strategies. But be aware that under different circumstances, we would have chosen different alternatives. So to summarize this pattern, template method enables controlled variability in our input handler algorithm to make it easier to process multiple operating nodes, succinct mode, verbose mode, and so on, which helps to enhance systematic reuse. It's also worth remembering that template method and strategy can often be viewed as pattern complements. They tend to be at duals of each other. You can use one versus the other, and it requires some deeper domain analysis and some awareness of both patterns and their liabilities and their benefits to know which one to select in a given circumstance.